Standard enthalpies of formation. So 3 ways to find delta H. One is you can actually measure directly or sort of indirectly from the surroundings by using calorimetry. The other one is using Hess's Law, where you have a bunch of known reactions that you can manipulate in a way to sum together to give you a target reaction. And by using those known enthalpies, you can find the target reaction's enthalpy. And not really a different way, but sort of the same way as Hess's Law, just a particular way of going about it is using the standard enthalpies of formation. So what this is again, an enthalpy for a particular reaction, and we're using a formation reaction to do that under standard conditions. So it is essentially the theoretical delta H for the formation of 1 mole of a compound from its elements in their standard states. And so as long as you've got all those boxes checked, it's a formation equation. So standard states, for example, they would be at room temperature. So if it's oxygen, it's going to be oxygen gas. If it's a metal, it's most likely going to be a solid unless it's mercury. Then there's particular solids where if they do have different allotropes, it's going to specify the particular allotrope in the stated standard formation equation. So how you'd write these formation equations, again, as long as you tick off those boxes, you've got a formation equation. So you're going to start with the reactants in their standard states. You're going to write the product in its particular specified state, because if you're making a solid product, let's say solid, water versus making liquid water, there's obviously an energy difference between those two states. And so you'd have to have a particular state that you're talking about. And it has to be for 1 mole of product, because we're going to be using a data table that has these values in it, and they are for 1 mole of a particular product listed. So if you looked at the formation equation for carbon dioxide, as long as we think of all the things that are in a formation equation, we can easily write one. It's a compound, and we want to make it from its elements, 1 mole of it, from its elements in their standard state. So we'd have to have carbon as a solid, we'd have to have oxygen as a gas, and we'd have to have them producing 1 mole of carbon dioxide. So this is what the standard the formation equation for carbon dioxide would be. You take carbon, you take oxygen gas, and again, you have to make sure you're making 1 mole of product, because that's what the data tables that we're going to refer to are listed for, 1 mole of product. And again, standard state for carbon has to be graphite, but the other ones are pretty easy to figure out. You can even look on the periodic table. It's often mentioning what their states are at room temperature. And again, make 1 mole of product. So formation of carbon monoxide, again, since it's 1 mole of product, you'd have to be combining with half a mole of oxygen. If you wanted to make the formation equation for methanol, again, you're making it from carbon and hydrogen and oxygen. You just have to make sure the carbon and the hydrogen oxygen are in their standard states at room temperature, and that you're making 1 mole of product. So the coefficients you end up putting in front of your reactants have to balance out to give you 1 mole of product. If it was for aluminum oxide, again, just 2 elements, put them in the right state. Make sure that they balance out to give you 1 mole product. And what you have is a formation equation. So these standard formation equations have particular delta H values. And instead of listing every single reaction, what we can do is we can just write down the compound that we're talking about, because we all now know what a standard formation equation would be. So we can just forget about what the reactants would look like and just write the product and say, okay, for methanol, here is the formation, the heat of formation for that particular compound. And we understand that it must have come from its elemental reactants in their standard states. So we use this data table, and then we are just given the delta H values for various different compounds. So if you look them up, you can say, okay, well, here's the formation equation for carbon monoxide that we wrote earlier. So you can look up on a formation equation table that gives you the heats of formation, and it will say the delta H, the heat of formation for that particular reaction, is negative 110.5 kilojoules. If you look up the one for methanol, it'll say 239.1, negative 239.1 kilojoules is the heat of formation for methanol. And again, the table won't write the reactants, it'll just say methanol's heat of formation is negative 239, because you know, without having to write it all down, since this is a standard enthalpy of formation, you know the reactant side of it, so you can just ignore that and get on with figuring out what the heat of formation is. If you looked up aluminum oxide, it should give you negative 1675.7 kilojoules to make 1 mole of aluminum oxide from its elements in their standard states. And do note that if you have an element, essentially it's a formation equation, the process necessary to make it from its elements in their standard states would be the exact same thing. So obviously, to make an element in its standard state from elements in their standard states is not doing anything, and therefore the heat of formation would be 0. You're not actually doing anything. So why we do this? With Hess's law, we take known equations that have particular species in them that we want to end up in our target reaction. So essentially, if you have a heat of formations table, it has a whole list of compounds and their delta H's. What we can do now is we can actually take those formation equations for any compound that we want to find a target reaction for, any compound that are in our target reactions, and we can put them together and get a delta H for any target reaction. So essentially, these are a list, a whole big long list of given equations for which we have the enthalpy values. So let's say this is our target reaction, and instead of before with Hess's law where we're given a bunch of equations already and we have to manipulate them and rearrange them to sum up to give us our target reaction so that we could find the delta H of this particular target reaction, what we can do now is that we can say, okay, well, let's just look up this compound here in our heats of formation table, and we know that we can take a formation equation for that particular compound, and we know what the delta H is of it. And then we can look up the formation equation for this compound and for that compound. And essentially what we're doing is we're writing our own given equations that we can then sum up to find the delta H of the target reaction. So for example, this hydrogen sulfide, we can say, okay, well, I know on the table it says the heat of formation, so I look up this on a formation table, and I'd say, okay, the heat of formation is negative 20.6 for hydrogen sulfide. And I know that particular reaction is when you make hydrogen sulfide from its elements in their standard state. Then I can say, okay, well, let's just quickly put up oxygen. So oxygen's already its elemental form in its standard state, so that's not going to require any energy at all. I'll just write the equation up here for fun. But sulfur dioxide, I could write it as again, if I wanted to make sulfur dioxide from its elements in the standard state, the energy involved in that reaction is given on this formation table, heats of formation table. And I can do the same thing for water as well. And I'd say, okay, there's the number from the table, and here is the formation equation. So essentially what I've done is I've written my own given equations, which then I can add up to give me the unknown delta H for my target reaction. But don't forget, we have to manipulate in a way that gives us our target reaction. So for example, there's 2 waters, right? My equation only has 1 water, but that's no problem. I just need to double that equation. Sulfur dioxide is here, and again, I need 2 of them because that's what it says here. So again, I just need to double my reaction. This hydrogen sulfide, I do need 2 of them, plus I need to flip the reaction, so I just need to multiply the whole thing by -2. And as long as I apply those changes to the delta H's as well, it should sum up to give me my target reaction. So the first one, let's multiply by -2. Let's pretend we're multiplying oxygens by -3, but again, it's not really a change, so it's, -3 times 0 isn't anything. The second one, we need third one, we need 2 of those sulfur dioxides, so we'll multiply by 2. And the water, same thing, we need 2 of them, so we'll multiply that by 2 as well. So let's do that, apply the changes. There's our 3 times 0, and this is going to be our given equations rearranged to give us our target reaction, because if we look at it, we say, okay, the 2 H2S, the 2 hydrogen sulfides are there, the 3 oxygens are there for fun, the 2 sulfur dioxides and the 2 waters are on their product side. I should check to make sure everything else is going to cancel out, so my 2 sulfurs will cancel out, my 2 hydrogens will cancel out, and I have my 3 oxygens canceling out with my 3 oxygens, which is fine. And actually I end up with these guys summing to give me 3 oxygens. My hydrogen sulfide, and on my product side I have 2 sulfur dioxides and 2 waters. And all those changes have been applied to the delta H's as well. So now we just need to sum them together to find out what their delta H would be. And there we are. We have got our target reaction, and sum up the delta H's, and it is negative 1036 kilojoules. So we don't need to be given target reactions anymore. We don't need to given reactions to find our target reaction anymore, because we have these delta H values from a table, and we know how to write our own formation equations that we can then add together to give us our overall target reaction. Now, think about what we're doing mathematically, and we can essentially do this all in one step. Here is the summation of heats of formation equation. Great sounding equation, and it is essentially what we just did, done in one step. What we're going to do is, if you're using those formation equations, the reason why we did them is that we wanted them to sum to give us our target reaction. And so essentially mathematically all we were doing is we were taking the products and we were minusing from them the heat of formation of the products, we were minusing from them the heat of formation of the reactants, multiplied of course by how many we're dealing with, multiplied by their coefficients. So we can now do this in one step, because remember that the products were the ones that were already on the correct side. The reactants we had to flip, so we're subtracting the heats of formation of the reactants from the heat formation of the products. So essentially we can do this all now in one step. We don't have to even write the reactions. So here's the exact same question. We've got our target reaction here. And what we can do is we can say, okay, well, let's take our reactants here, and again, oxygen's heat of formation is 0. But if we take our heats of formation of our products and we minus the heats of formation of the reactants from those products, we should get the same answer. So we're going to take the heat of formation of 2 sulfur dioxides and the heat of formation of 2, importantly, gaseous water molecules, and again there's 2 of them. So that is the heats of formation of our products. We're going to multiply them by the coefficients, the fact that we're dealing with 2, and that's kind of like what we did when we wrote the reaction out. We've multiplied the delta H by 2 because we needed 2 of them. We're going to sum that together, and then we are going to subtract from that the heats of formation of the reactants. Now, waters is 3 times 0, so that's easy to do. And there's 2 sulfur dioxides, so take the heat of formation of the 2 sulfur dioxides, and we should end up with the delta H of the target reaction. So plug in the numbers, we get the same thing. It's the same process, but now we can do it in one step using the summation of heats of formation equation, which means from now on, as long as you have a table that shows you the heats of formation of species that you're dealing with, in one step, you can now find the delta H of any target reaction. So let's try it out. How much energy does it take for plants to make glucose? So if we look at the process for making glucose for plants, we know they take in carbon dioxide and water, they make 1 glucose, and they produce 6 oxygen. So that's our target reaction. And as long as you can find these species, and again, oxygen being an element, its summation, its heats of formation is going to be 0. But as long as you can find the other species in your heats of formation table, you can do it all in one step. So look up carbon dioxide heat of formation, look up water's heats of formation, and look up glucose heats of formation. And we're going to take glucose heats of formation, multiply by its coefficient, and subtract from that the reactants heats of formation, and we should have the delta H of this reaction. So there's our summation of heats of formation equation, and again, products minus reactants. Find the heats of formation of a glucose, and you can add in 6 times 0, and you're going to subtract from that 6 times the heat of formation for carbon dioxide and 6 times the heat of formation for water, and you end up with an enthalpy value of positive 2,802.7 kilojoules.